Hello, everyone. So welcome to 189. So this is our first industry speaker, and so it's exciting to have Dr. Shreemoy Mishra from IOB Labs, and he has a very exciting background. So he got his PhD from UT Austin in game theory and economics, and he's been not only he's been teaching, but he has worked in different industries and exciting researches that he has done over the past years. And in particular, he's now been focusing into Bitcoin. And given his economical background, I think that would be very exciting to have him. Please take it away.
Well, thank you. It's great to be here. Okay, great. So, yes, as Mo already mentioned, I'm an economist, a former academic economist and engineer. I'm a researcher at IOB Labs, which is associated with the RSK blockchain. So if you are familiar with the Ethereum Foundation, that's separate from the Ethereum blockchains. That's sort of the relationship between IOB Labs and the RSK blockchain. In short, what RSK tries to do is allow people to run Ethereum-type smart contracts, but using Bitcoin. That may not make a whole lot of sense to those of you who are just getting started in this field. So let's just carry on with the agenda for today, which is just to talk about some basics of Bitcoin. And yeah, I should thank Cameron and Mo and also Meher for this chance. I think it's going to be a fun for everyone. So let's see. So I think last meeting, I was here for your Thursday meeting for the first 10 minutes, and there were some questions. One of you asked Mo if there are any prerequisites for this course. And while there may be prerequisites for the course, in general, the industry doesn't really have any prerequisites. And that's because it touches on a whole lot of different areas in economics and computer science and math and crypto. Also, there are social and legal implications of blockchain technology. So there's no specific background or prerequisites as such. Almost everyone is self-taught to some extent in the field. So I'm just listing some of the areas that people have expertise in, but you always have to expand your horizons if you want to be in blockchain. So I'm going to just quickly check if there are any conversations in the chat. Nothing there. So keep going. Here are some links in case I lose my mind or if I lose the internet, which did happen 10 minutes back. Here are the links to the slide itself. And for later, in case we don't cover everything that I was thinking about, here are two links. One is the original markdown for these slides and a simple IPython-based Jupyter notebook, which you can find on this GitHub link. So you can look at that now or later as we go on. In terms of what I was expecting from the students who are here, just basic awareness of the idea of what a cryptographic hash is. Not the technical details, but just the idea that these are one-way functions, which are nearly impossible to invert. And also that there are no practical collisions. In a way, you give an input to a hash function, the output is sort of unique, or at least we don't know of any collisions. The second idea that I assume people are familiar with at just a very top level is private public key-based cryptography. So here's a simple example in Python, for example, that uses 3 variations of a string, the binary version of a string, to generate hashes using the SHA-256 hash function. And you can see small variations. In the first variation, I add a space here next to the E. And another example, the E is dropped. And even small changes in the input have a big change in the output. These are the hexadecimal versions of the output. And so we'll be relying on the SHA-256, which is the primary hash function for Bitcoin. So what you'll be seeing on block explorers and in the field a lot is the hexadecimal format, which If it's a 256 string of binary, then that's 32 bytes of data, which just comes out to be 64 characters long in hash. And we'll be seeing this a lot. And for the basics of the public and private key cryptography, some of you may be using SSH to authenticate into your GitHub repos. Authentication is not that much of an issue in Bitcoin or encryption. The main issue here is signing transactions. So that's going to be core here. Keys, as you may know, are just very large integers. The private key is generated from a pseudo-random number. And once you have the private key, we use that to generate a public key. The specific ways depend on the standards we use. There are a whole variety of standards. But the critical thing here is even if your public key is revealed, there's nothing anyone can learn about your private key. Lots of different mathematical structures are used in cryptography, which I'm really not well versed or an expert to talk about. But what I do know is there's special rules for arithmetic. So adding keys and subtracting keys, multiplying keys. What do you do when you add two keys and the resulting key is more than 256-bit? So you need to have rules for overflow, how to handle those. So those are special rules for the mathematics for managing keys that we won't get into. The specific standard used in Bitcoin and also Ethereum is a class of cryptographic keys in a family called elliptic curves. And the signatures are denoted by a pair, typically R and S. The first time I saw this, I'm not a crypto person, I was really surprised. I always thought signatures were just one long string of bits, but it turns out in ECDCA, signatures are a pair. And those of you who are familiar with Ethereum will actually see that signatures in Ethereum and also in RSK have three components. In addition to the R and S, Ethereum added another component, V, for some security purposes. At this point in most Bitcoin introductions, you'll see a picture like this for ECDCA, elliptic curve cryptography. I find these pictures in a short talk to be quite misleading, so I'll skip it and leave that for a crypto talk. But the interesting part is in Bitcoin with ECDCA, each private key is actually, it can be used to generate two public keys. And so two addresses. We'll see in a bit what an address is. Here's a simple Go example of signing a message. The first library here is just appealing to a specific standard and a specific type of curve within the standard, a random number generator to get us started with. And so here's a simple example, mostly based on Go source manual. Maybe the GitHub version is easier to see because it's at one place. So this just demonstrates a simple process that we start with a random number, then use elliptic curve cryptography to generate a private key. In ECDCA, the private keys have 2 bits, R and S. We use those to sign messages. The message here, for example, is a byte version of some string. And then it's easy for people to verify that the keys used to sign the message belong to the public key associated with it. It's very hard for me to kind of not get any feedback from the Zoom call, so I'm just going to occasionally check. So here is a question. Why do we need arithmetic on keys? From Masa. So this is a question better suited for a crypto person, but my understanding is this. We use a pseudo-random number generator to get a private key, and then we make computations on this private key on the elliptic curve, say add this 10 times to itself, or subtract some number from it. So you start the private key and do arithmetic on it to get your public key. And the steps to be taken are part of the standard. So that's my top level answer of why we need an arithmetic on private keys. How do we ensure a function is one way? That's sort of the definition of a hash function. Is it's almost like taking everyone's names and putting it into bins for the letters that the names start with. So we'll have 26 bins. So if you pick the bin for A, all you know is that it contains names of people whose names start with A, but you can't recover the original input that you gave it, everyone who has a name starting with A. So it's one way. I think this reminds me of a different question of how do we know there are no collisions? Because you couldn't possibly try every combination of inputs. That reminds me of the story of how 10 years ago, maybe, Google found a collision in SHA-1. And so SHA-1 is no longer considered secure. But SHA-2, as far as we know now, no collisions have been discovered. And so we're fairly confident that if you change the message, the input to a hash function in any way, it will be detected. It will lead to large changes in the output. So 2 fantastic questions already. Just maybe stop for 20 seconds, not 27 seconds, to see if there are any more questions on the chat. Are there comments on clarity, speech, if you need me to speak louder? 2 more seconds. Why is the arithmetic to generate a public key not reversible? I don't even know if that's true, if the arithmetic is not reversible. Since the arithmetic follows a protocol, it's an algorithm. So the algorithm should be reversible, but modular arithmetic with overflows hides. If it was predictable deterministic math on the space of real numbers or all integers, including up to infinity, then you could invert some functions. But this is a specifically defined mathematical field, and so it's hard to recover the inputs from the output, even if you know what the steps are. And about a long time ago in grad school, my teacher told me it's better not to answer some questions. So I think rather than pretending to be someone who knows crypto, I should just not go there and just say I don't know. Let's wait 3 more seconds to see if there are any other questions. Right, so keep going. On here, moving on to Bitcoin, the reason why most of us are here, that's what got this field started in blockchain. If you go to the Wikipedia, not Wikipedia's page on Bitcoin, but bitcoin.org has its own Wikipedia page. Sometimes it has outdated information, but at least from my point of view, it is mostly free of bias. There's no one selling their own blockchain. So here is something I'm quoting stuff from. It's not the first cryptocurrency, not the first distributed cryptocurrency, but it's the first widely successful implementation of a cryptocurrency. Idea was described earlier by Wade Dai, and both of those names, the first name and the last name of the researcher, are now used for different units in the Ethereum blockchain. And the second part of the statement is it was the first successful implementation using cryptography, and there's absolutely no reliance on any central authorities. And the question for you all is, are you comfortable with the idea of what a central authority is? I think the reference here is to like a Federal Reserve Bank that issues currency. Are there questions about central authority, or not so far? So let's keep going. A lot of folks are very interested in the history of Bitcoin and the motivations and who founded it. Was it an individual or a group? I really don't care so much about it. I do care about the motives, but not the identity. So we'll not get into the speculative stories or if Craig Wright really is or isn't Satoshi. But what we will think about is it's a fun idea, a peer-to-peer monetary system. So since it doesn't have physical currency, the currency can have any kind of denominations. You can choose what it says. In Bitcoin, for example, you can have numbers as small as 10 to the minus 8. Bitcoin. That's the smallest integer. The 1 in Bitcoin represents 100th of a million Bitcoins. And so that's called a Satoshi. Coins are just digitally signed messages. And when you sign a message, and you basically transfer ownership of your coin to whoever you are giving it to. And they can have nearly arbitrary value except this lower bound here, 1. Let's have a simple example here. Someone gives you 2 coins worth a cumulative 7 Bitcoin. That's a lot of money these days. It's about 10,500, I think, today's price per Bitcoin in dollars. So what you can do is you can create a coin using these 2 as inputs and pay 4.5 to someone. Of the remaining, you can redirect 2.4 to yourself in a new coin. And whatever little residual amount is left, 0.1 is not so residual, it's not so little anymore, it's still $1,000, goes as a transaction fee to people who create blocks in the blockchain. We'll come back to this example in a little while. And before I check for questions, I'll just put this slide on there to say the fundamental security problem in Bitcoin is double spending. There are some other concerns like people censoring transactions or privacy issues, but the primary issue, the primary security issue is this. Someone pays you 100 coins, that's a signed message. Someone then uses the same coins and either pays somebody else or they send it to themselves. So that's a second signed message. And then they try to convince others that the first message, which was a payment to you, is invalid. So that's called a double spending problem, and that's a primary problem in blockchains. Let's check for some questions here. Good.
Yeah, sure. I think everybody, we could just ask question on the mic, so that would be easier, so you don't have to keep checking back either.
Okay. Yeah, so we can do that.
Yeah, hi.
Yes.
Professor Mishra. Sorry about doing your name. I'm so sorry.
It's fine. You can just call me Shree.
Can you go back to the previous slide? Yes. So I'm confused about the concept of coins. So when we do transactions, let's say Bitcoin, does one coin represents can a coin represents different values? Like it seems here
yes.
a coin have like.
Absolutely. It's not like a dollar in physical currency which says $1 or 5 or 20. Here, these coins are just messages, so they can say anything.
Okay, so what you mean is two coins value can be different. Say one coin can value $100, the other can value like say 1,000.
Yep. The only restrictions are really that the value cannot be less than the number 1, which represents 100th of a million of a Bitcoin. So the lowest value is 1 Satoshi. But in terms of payments, there's no idea that a coin must be worth a certain number of Bitcoins. It's completely abstract.
Then how do we know the value of a certain coin?
So think about a transaction in which you spend Bitcoin. Before you spend Bitcoin, you get Bitcoins from somewhere, right? Either you buy it on Coinbase or someone sends you some Bitcoin. Are you cool with that?
Uh-huh.
Right. Now, when you get those Bitcoins, let's say 5, there's no specific way of getting to 5. You can receive 100 transactions that cumulatively give you 5 Bitcoin. So each of those will have denominations that can be completely arbitrary. As long as those integers add up to 5 Bitcoin. So the system really works in terms of inputs and outputs to transactions. Every input to a transaction, so if you get 100 inputs, each of those inputs is really a coin. And if you use these 100 inputs to fund a single payment to someone, you have just combined all these inputs, it's fungible, to create a single coin worth 5. So once the inputs are added within a transaction, they lose any meaning of where they came from. It's just one sum. and then it's up to you, the spender, to see how you allocate them. If you you know what? Hold on to this question. Maybe we'll see some block explorers in a bit.
Yeah. Okay. Thank you.
And then it may help clarify. It's really misleading to think of a coin as a specific number. Just think of it as transactions having inputs and outputs.
Okay, great. Thank you.
Sure. So we'll revisit your question in a bit. Just to remind you where we were, the fundamental security problem is double spending. And if it were not for this cheating problem, electronic currencies are quite simple to create. It's just about databases. And so we don't want to allow multiple histories. We want to find a system that allows us to agree on a single history. Another bit of jargon here, just to talk about addresses, because they differ across blockchains. Bitcoin was the first. So the way Bitcoin addresses work is you start with your public key. We hash it first using SHA-256. That hash is then hashed again with a different hash function. This is one of the few instances in Bitcoin in which the double hashing does not use SHA-256 twice. Usually, most hashing in Bitcoin is use SHA-256 two times. That's not the case in the first step of address generation. So once you've done that, we now have an output that is 160 bits long, so that's about 20 bytes. To that, we add version number and a checksum. The checksum and the version number, and finally, a base 58 encoding. So if you're lost here, there's three things to take from here. First is, this is one of the first unusual cases of not using double SHA, but a different hash function, a SHA combined with a RIPEnet 160. The second thing is the use of a checksum, which prevents users from accidentally sending money to invalid addresses. So checksums help confirm that a Bitcoin address is valid. And base 58 is, it just expands the number of characters we can use to denote addresses. Because if it is just hexadecimal, then we have 16 choices of characters. If we use the entire alphabet A to Z, then we get 26 and 26 more for uppercase, lowercase, the numbers 0 through 9. And what Satoshi did was, he says, to avoid confusion, let's not use the uppercase or lowercase o, and let's not use lowercase l or uppercase I to avoid confusions with 0 and 1. And so that's base 58, and that's how a Bitcoin address is created from public keys. A transaction, closer to the question asked a bit ago, a transaction is just a transfer of a bunch of coins. How many coins? That depends on how many input transactions are there for the one, and how many recipients there are to the funds. And instead of coins, it's much better in Bitcoin to think about how much of the transactions that you receive Bitcoin in, what have you not spent yet? And so what you'll see often is a reference to UTXOs, which stands for unspent transaction outputs. Some more jargon, a block. A block is just a container of transactions. The transactions can come from anywhere in the network, and they are constantly transmitted, but blocks are produced about once every 10 minutes. And so blocks are just containers for a batch of transactions. Who creates the blocks? Those are, as you may be aware, are people called miners who create blocks. And finally, we somehow link these blocks together, kind of like a single linked list, but the linking is done through cryptographic hash functions. And we'll see details of that coming up in a bit. So the blockchain is just hashing blocks together. The goal, of course, here is to agree on a single historical record of transactions. Here's an example back again. 2 inputs, 3 and 4. So those are 2 coins, one coin containing 3 Bitcoin, another containing 4. And there are 2 outputs from the transaction, 4.25, I pay to someone, 2.4, I redirect to myself. So I've mixed the coins these 7 coins together within the transaction and created 2 new coins, one for 4.25, another for 2.4. The residual goes to the miners as a transaction fee because these add up to less than 7. The only requirement is that the sum of all output has to be less than the sum of total input transactions, and the difference is collected by miners as a fee. Let's go to an explorer here, in which there are lots of different explorers. I just picked one for an example. And we're looking at a specific block that is at a block number 650, 750. A block number is also called a block height. So let's go here. That is the hash of the block. You'll see it's a number that starts with a whole lot of zeros. That's the height. It was mined by a group that goes by the name F2 pool. We'll see some of these other stuff later, but let's come here to see and look at the transactions. This transaction here has one input, that's 1 coin, and it has 2 outputs. Those are 2 coins. And here you see what these coins are worth. So that is sort of related to the question you asked earlier. I'm sorry I didn't catch your name.
You can just call me Jason.
Jason, so if you see the block explorer here, any of these transactions, you can just count the number of inputs and outputs, and that's one way to interpret what the coins coming in and out are. And you can see these coins have vastly different numbers on them. This one here is worth 0.001. You can convert it to dollars. And just quickly see some questions here. What does the game source mean? I was just trying to be cute there and say, let's say I want to pay someone for the source code to a game they developed. This wasn't the example I was trying to make for double spending. I paid them 100 Bitcoin for their source code, and then I send the same coins to myself later in a different transaction. We want to avoid those situations. I don't see any other text questions here. So linger here in the block explorer for a bit. All these transactions in this block 65750. A lot of them are usually, so this one also has a single transaction. If you look at the details, you'll find several that have more than one input and several output. This one, for example, has 4 different outputs. So these are just coins in vastly different denominations. Some of the things that we care about, especially to understand how security works in Bitcoin, is to look at specific fields from the block. Specific fields we care about are the hash of the block, the timestamp of this block. So for example, the block I'm talking about is from the last day of September. The Merkle root, we'll get a bit later into what the Merkle root means. And version and nonce. The nonce is something that's entirely different in Bitcoin and Ethereum. So those of you who are familiar with Ethereum, this is a different nonce. And we care about another number called bits, which we'll see is related to how difficult or easy it is to create a Bitcoin block. The reason I've put these things in bold is because that's what we use for security in Bitcoin to generate a block's hash, which is also called a proof of work. Okay, how about now?
Like it's working now. Perfect.
All right, so we can do this again. If it happens, we have a solution.
This sounds good.
All right, so was Jason had a question about a slide, or do we?
No, I wasn't having a question. We just simply couldn't see the slide.
Couldn't see it. Yeah, it's horrible. All right, here, let's keep going. So some of the things you can see here, this tram, it has nearly 3,000 transactions, and the block reward and fees together are that much. If you kind of do that computation, you'll find that the average transaction in those blocks, and that's fairly true of recent blocks, costs about $2.20. So not exactly cheap. Bitcoin transactions used to be quite reasonable, and that's one of the reasons I did not include any points from Satoshi's introductory section of his paper, because one of the things he wanted to stress on was the possibility of doing micropayments, small payments, And that's really gone out of the window with Bitcoin. Although second layer solutions, which you'll learn about later, like Lightning, are trying to change some of those problems about transaction fees and batching. So the average transaction fee currently is about $2. And for the interest of time, I'm going to skip some questions, just ask you, what do you think is the smallest number? But as you see, most computer scientists have no trouble saying 0 as the first number, so we'll just go there. And in the interest of time, does anyone know what's special about block 0 apart from it being the Genesis block? There was a message in block 0. Does anyone know about the message in block 0?
Do you mean the message that tells everyone that this is the first block and this block has no parent? So
that's one. So if we go to the block, this is block 0. And here's the initial block that paid 50 Bitcoin to the miner, which obviously was Satoshi himself or themselves. And the input to that block, obviously, since nothing was there before, is some arbitrary data that Satoshi put in. Now, some of you would have seen this before. And these are actually characters that we can convert to ASCII to see a message from Satoshi in. So some of you know this already. For the others, it may be a little bit fun. And here is the message that he left us. The context here is the crash, the financial crash of 2008, 2009, where the banks were bailed out. And so he left this piece of this message in the Genesis headers. That gives you part of his motivation, which we don't need to speculate much on, was the idea that our trust in banks is, that trust is fragile, the banking system is fragile. And so he wanted to build a system that does not rely on trusting any person or any institution, purely peer-to-peer. So that is the message. Let's go to the paper, which we'll spend a little bit of time on. We're at 5:22. I'm also on the West Coast here, so quick check for questions. The chat. All right. And now for some reason I can't see the chat. So if there are questions, someone would you please jump in or tell me that there's a question, because I can't.
I'll just let you know. I think everyone from now on, I think, just going to speak out their question.
Yeah, that'll be.
I will read it.
Yeah, that'll be great. Thank you. The motivation in a pure P2P cash system without the need to trust anyone. Digital signatures are necessary, but they're not sufficient because of the double spending problem. And the solution Satoshi came up with was use transaction timestamps, so that if I send two conflicting messages, in the first one I paid someone, and the second one I paid that money to myself, we can have an ordering system that says, hey, this one arrived first, and so we're going to discard all other messages. We'll just think of the first one as the valid message. The problem, of course, is if you send a transaction from Portland, it's going to arrive in Davis faster than a block from Korea or South Africa. And so we need to figure out a system of ordering without relying on actual time in which a packet, a transaction, or a block arrived on your computer. And so that's what we need to look at, is a system to agree on ordering transactions that will be batched together in a block. And we want to create cryptographic links between these different blocks, which was going to make them very impractical to falsify. The key word here is impractical, because a lot of marketing departments in blockchain companies like to sell blockchain as irreversible. And that's not true. It is possible to reverse blockchains, and reversals happen all the time. It's just that it's impractical. Computationally impractical, monetarily impractical to try and reverse the history. And essentially, rewriting blockchain history, how easy or how difficult rewriting a blockchain is, determines how secure that blockchain is. Some of you may be aware of recent double spending attacks on a blockchain called Ethereum Classic. They were attacked about 3 times in the past 6 months, and now they are moving from their proof of work system, which relied on SHA ETH hash, to a new system based on SHA-3. So the security is all this tied to how easy it is to modify the record. Okay. So what you want to do is, if you want to think about changing a single block from a year ago, then you can't just replace one block and plug in another. Any block that we want to rewrite, starting from that point on, we have to rewrite the whole chain. And that's what makes the task very difficult, because to do that, you have to outcompete others. And right now, I think my estimate is that the system overall spends about $10 million a day to create blocks. And so if you want to gain a majority of that hash power, computing power that's needed to offset the other nodes, then you need to be spending at least $5 million a day and trying to outpace everyone else and rewrite history. I'm skipping some details here, so the math is not exactly going to be right. But the point is, it's often going to be a lot more profitable to just keep mining. If you have those resources, 5 million a day, spend that on mining or something else rather than trying to rewrite Bitcoin. Because at most, all you can do is just double spend your own coins. Even if you have 100% of the hashing power or computing power, you can never spend someone else's coins. But for other blockchains that have less security, less computation power, like Ethereum Classic, it's still possible for people to attack them and reverse transactions. Another thing you will often read about Bitcoin is that the majority of nodes working together leads to what's called the longest chain. I would encourage you to interpret the longest chain as a heaviest chain. Heaviest being measured in terms of computation power that went into forming the chain. We'll see an example in a bit. Satoshi provided in his paper simple examples using the Poisson distribution and C code. So those of you who are familiar with Poisson distributions, they're often used for count processes. For example, the number of buses that arrive within a 1 hour window. The Poisson processes are very convenient to work with, and he uses them as illustrations to see what would happen if a Bitcoin network is attacked with rival computing powers, and how much of a gap do we need and how much power they would have to spend to offset the honest nodes. Another great thing about the network is that if you're running a node, you don't have to be online all the time. Nodes can stay online or go offline and rejoin as they please. Just like whenever they rejoin, whether it's after a day or after 5 years, they just accept the then current longest chain as the true chain. And they treat that as evidence of what happened in the network when they were offline. A transaction is, coins are just digital signatures. We've talked about that before. And one thing that's kind of confusing to people is you don't have to do anything to receive Bitcoins. All the actions of signing and cryptography are really about spending money, not to receive it. So if you want to spend some coins that you got in a transaction, then the way you spend coins is by using your private key to sign the transaction. And you unlock the funds of the input transactions, how you got the money, and that's how you create, that's how you get to spend. So step one is whatever transaction you got the money in, you use your private key to unlock those funds tied to the transaction, and you must specify who the funds are going to. And doing so, you create a new coin, or as many coins as the number of outputs in your transaction. So just to remind you again, you got nothing, there's nothing to do when you're receiving coins. They will just stay there in the records. The only conditions are on spending. Anyone can verify signatures, and so the chain of ownership, so when you spend money, people can see where you got the source of your funds from, which transactions you got the money from, and which transactions those came from, which blocks those came from. So the whole chain is auditable. But of course, only if you have access to the full database. Not everyone runs a full node. It's not practical for most people. So let's kind of speed up a bit and get to what the solution is to avoid double spending. So Satoshi thinks of Bitcoin network as essentially a peer-to-peer time server. What it's going to do is timestamp transactions that are batched together in a block. And all these transactions that are in a block together will use some data from the block to compute a hash and share that hash all over the network. The hash of the block will prove that the transaction that you're specifying was known at the time when the block was created. And so if there are two competing transactions, all people have to do is figure out which block showed up first. And since we have a linked list of a chained set of lists, they have a specific ordering. It's easy to show which transaction happened first. Any reuse of funds will be rejected. And the idea of how to prove that something was included, that spending some money you sent somebody was included in a block, relies on an idea called Merkle trees and Merkle proofs, which we will see in a bit. So the job of the network is to act collectively as a timestamp server. Another thing that at least I found confusing at first was the use of the word timestamp. When I think of timestamp, I'm thinking of 30th September, 8 o'clock. But that's not what Satoshi means by a timestamp server. The hashes are really the timestamps here. And it's okay to use a block number or a block's height to reference when a transaction was included, because those are unique. A block has a unique number and a unique hash. But no one really talks about the actual timestamp in terms of date and time. So think of a timestamp as the hash. Stop for 5-6 seconds to see if that jogs the memory of any questions.
Yes, I have a question. So when we don't talk about exact time in Bitcoin, right? We use hash, but how do we tell two hashes, which one is earlier, which one is later?
So let's say you mine a block and I mine a competing block. If you mine the block, and these are very close in time, within seconds of each other, your friends who are closer to you in Davis or in California will get your block first before they see mine. Right? So ties like that happen all the time. And if there are two competing blocks competing for the same height or same position, what happens is the network, the node, will calculate which of the two hashes required more computational work, and they'll accept that. So if the transaction you packed into your block and the hash computation you did, essentially if your hash is more zeros, for example, then you win, I lose. Does that make sense?
Yeah. It's
so that's how ties are broken.
Yeah, thank you.
Yeah. Sure. And what I would like to do at some point, depending on where we are in the clock, is walk you through a simple example of what it means to compute those zeros. So basically what it does is a block has lots of information, like you saw on the chain for 650, 750 there. And we will use some of that information to create our hash. So what we'll use are, maybe just go with the example. Is this something you all can see? Is this visible? This.
Yeah. Yes. We can see.
Oh, okay, good. Thank you. Because I can't see the chat, so. So what this is a simple exercise of using that block that we saw in the Explorer. We'll use some of the information from the block to compute its hash. And that essentially will tell you what mining pools do all the time. This is what mining is basically about. So you pick a block number, and there's lots of APIs that you guys can use. I used this one. I did not use the Explorer that I was just showing you, because in the Explorer, the timestamp was leaving out seconds. It was only showing hours and minutes, but part of the protocol needs Unix time that you need the whole access to. thing. So from the block, these are some of the fields: the hash of the block's height, the fees, what's the total size of all the transactions in there. So from these, we need to use 6 of them to compute our block's hash. These 6 fields are the version, which is 4 bytes, the hash of the parent block, the previous block, that's a hash, so it's 32 bytes, because all these hashes are SHA-256. The Merkle root, which we'll go over next, that's also 32 bytes. And these are in order. We also need the block's timestamp, 4 bytes. Bits, this is related to the difficulty of the mining task. So simply speaking, the more zeros you need out front, the more difficult the task is. So this is what kind of references the difficulty of mining Bitcoin, and the nonce. Okay. So if you are a participant in a mining pool, because it's just not feasible these days to be a solo miner with your own equipment. It just the only profitable way to mine Bitcoin is being as part of the pool. So what the pool operator is going to do is the pool operator has no choice on the version. The pool operator will have no choice on the hash of the previous block that's already been mined. The only choice is the mining manager they decide which transactions to include, and that will generate a binary tree of hashes of the transactions. We'll see later. But the root of that binary tree is called a Merkle root. The bits are the difficulty determined by the network, so you cannot choose that. The only degrees of freedom really are the nonce. That's 4 bytes. And the timestamp, you can play around a little bit with the timestamp. So there's very little degree of freedom. Most of it is concentrated on the nonce. So we use these 6 fields. We concatenate them, but before we do that, they should be in hexadecimal, and they should be in a certain ordering with the biggest number up front, called big endian. Okay. So here is, you just grab the fields. Once you grab the fields, this is the target that we want to match, that many number of zeros and that specific hash. So we've got 3 integers here for the version, the nonce, and the bits. There's a timestamp that we'll be converting into Unix time and then into a hexadecimal. And these hashes are already in hex. We just need to reverse the endian. The example in Bitcoin, the code example that I found on Bitcoin Wiki is a bit outdated. That no longer runs. So I just wrote some helper functions to speed up the process. We'll skip that. This example file is on the GitHub thing I posted earlier. And so all we've done is taking those 3 integers, the timestamp, and the 2 SHA hashes, convert them into big endian hex, add them all together, convert that hex string into an integer. That's converted to a byte. If you are following the description of the 6 fields, you'll remember that 2 hashes, that's 32 and 32, and the rest of the 4 are all 4 bytes each. So that's total 80 bytes for the block header that's being hashed. And once we hash it, which is of course in Bitcoin a double hash, that's the first, sorry, that's the outer one, and this is the inner one. And you grab the hash, this is what we get. And that's what's called a proof of work. There's only one more step left. We have to reverse the endianness, so the zeros are out in front. And this is what we're trying to match, and it matches, because I mean, it should. The first time it didn't match because I was using a different block explorer, which did not have seconds, so obviously the hashes won't match. And that's what mining pools are doing pretty much the whole time. They're computing hashes just like this. The manager gives them most of the information of those 6 fields, and the individual folks are varying the nonce. That's those 4 bytes. 4 bytes is, I think a computer can go through 1 billion numbers in a second. So with the modern mining equipment, this 4 bytes isn't really enough, so they add other randomness to it. But this illustrates how the sort of the lottery of creating a block is one. You do a double hash of those 6 fields in a specific way. There's lots of combinations, as you can see, SHA-256. And so the work needed in terms of computation depends on the number of zeros you want out front. So the more zeros we pack out front, the less likely we are to find a block. So finding a solution is extremely hard because you have to make lots of random guesses, and so we have specific thing. When Satoshi started this, Bitcoin mining was CPU based, then it became GPU based. Ethereum is still a lot based on GPUs, but Bitcoin went from CPU to GPU to field process programmable gate arrays and ASICs, which are application specific integrated circuits. That's
just a quick question.
Sure.
So why the double hash, as you mentioned earlier? You were doing the double hash.
Almost everything in Bitcoin is a double hash. I do not know exactly why. My understanding is we don't really know what the probability distribution of the SHA looks like. But one thing the double hash does is it allows us to make an approximation that all 2 to the 256 combinations are sort of uniformly distributed.
Okay.
Do you recall some other reasons for the double hash?
No. I was just kind of. I thought maybe there's some reasons I'm unaware of, but
so one of that
my
is
understanding was based on what you described as well. But I thought maybe there is some other factor as well involved.
Yeah, because I mean, we can't even imagine what this distribution would look like, right? So we hope that SHA-256 is close to being uniform, and using it twice just makes it. But then it can't just be about the proof of work, because the double hashes show up everywhere, including the Merkle trees, which we'll see in a bit. So I guess I should just say I don't know. I know one reason, but there must be many other reasons why double hash is used. Right, so implementing the system, we just walked through a simple Python example that showed you what the Bitcoin system does every day. The computation I showed you was one double SHA computation. The number of computations that happens is, I think I had it there. I'm not sure if I have it here. This is what the network is doing every day. 150 times billion such computations every second. So that's it's kind of astronomical. Well, it's beyond astronomical. We used to think of these numbers as astronomical, and now they're just bizarrely big. 75 billion block hash computations every second. So if you want to double spend the Bitcoin, that's the kind of forest people would have to fight with. Okay, I can't see the chat, so.
There's no chat. I'll let you know if there is any.
Okay, thank you. So part of the proof of work system is, in a distributed system, we are all competing to add transactions in blocks. And so the proof of work provides us with a way to say, hey, we have a winner. This miner gets to mine the next block because they have found the solution to the current problem. And when one block is mined, the hash changes. And so people move on to the next block. So the first part of proof of work is how someone gets to create the next block. The second thing is how everyone agrees that, yes, the problem has been solved. I mean, no one can force people. There's no one sending emails to say a block has been found. Move on to the next one. So it's up to each individual miner to either accept the system's broadcast or just keep working on by themselves. In a way, yes,
I have a question.
Sure.
So as you mentioned before, Bitcoin updates like approximately 10 minutes, right? So if we want to calculate a hash for a block, does it mean that that calculation process takes approximately 10 minutes?
Oh, no. We want blocks to be processed in less than a second. Like in RSK, our blockchain, we generate blocks every 30 seconds. Ethereum generates a block every 14 to 15 seconds. All those smart contracts, payments, whatever is happening there, the block is itself processed in less than a second. The rest of the time is communication. It takes a few milliseconds for the block to be passed around the network. So a Bitcoin block, the 10 minutes is just a choice.
Okay, so we spend a lot of time waiting, right?
Yeah.
Ah,
so your
okay.
Bitcoin node is not going to be running as hot as your Ethereum node.
So we actually get the hash for the block very quickly, and we wait for a long time, and then push the block to the chain, right?
Depends on what kind of node are you running. If you are running just a user node, you're not a miner, you just have your own Bitcoin node, then you're just receiving transactions, you're receiving blocks, and most of the time you're just forwarding the information to your peers.
What if
The actual computation is just a second. You're just forwarding, you're not passive. But forwarding blocks is mostly a network thing. You're not using so much CPU. But if you are a miner, then you are constantly processing blocks for two reasons. One is if you are one of 1,000 people mining as part of a pool, how do you know how you're going to share the rewards? Right? And so what they do is mining pools operate on the system of shares. If Bitcoin needs a solution with, say, 8 zeros out in front, what the mining operator is going to do is give you a target that only needs 5 zeros, which is more frequent, right? It's easy to hit 5 zeros than hit 8 zeros. So everyone that's part of a pool is trying to compute hashes that are less difficult because their share of their pool's reward is going to be based on how much effort they put. And so the question, it really is how much competition are you doing depends on what your role is. If you're a user, not much. If you're a miner or you're a participant in a mining pool, you are quite busy.
Okay, so what if I am a manager, say a boss of a pool?
I can't hear you. Can you speak louder, please?
Oh, I'm sorry. Let's say I am a manager or a boss of a pool, and I get a bunch of hashes beginning with 5 zeros. But how can I output a hash with 8 zeros, say?
Well, you can't. You just give the headers to all these miners who are working for you automatically. And by chance, some of those hashes will have 8 zeros. There's nothing that says a hash that needs to have 5 zeros cannot have 8 zeros.
Oh, I see.
You see? It's just that if the difficulty is set lower, you'll find blocks and hashes easily. And that's how our network, the RSK network, operates at 20 times the frequency of Bitcoin. We generate blocks every 30 seconds because our hashes are easier to find. But once in every 20 RSK hashes is good enough to meet the requirement for the Bitcoin network. And that's when that RSK block's tag or information is imprinted on the Bitcoin chain.
Yeah, I get it.
So so it's based on the system called shares. Think about hashes that satisfy less difficulty as the share or a fraction of the rewards you'll get as part of a mining pool. How many hashes with 5 zeros or 4 zeros you find? So we'll keep going.
So that's very interesting. Are you going to kind of capture that whole ecosystem, how that works? Is that something that you will be talking about?
I had the mining thing. It gets interesting because there's lots of strategic game theory in there.
Okay. Maybe just just give a picture of just the overall picture, not the details of it. Maybe like
because I can give you the reference. It's a paper by Manny Rosenfeld, 2012, which analyzes it. But yes, so let's take a time check. It's 5:50. Let's once we're done with the Merkle proofs.
Let's continue. You're right.
What we can do is let's see where we are when we get to the Merkle proofs.
Sure.
And at that point, we can decide which way we want to go, depending on how much time we have.
Sounds good.
Okay. So the main ideas so far have been using 6 fields from the block header to generate a double SHA hash that meets some target. If it meets the target, that miner gets the block, and everyone else moves on to the next one. And everyone, importantly, who agrees must point their effort, the next block. So when a block is found and you agree that it's been found, you move on to the next one and you point your block, the one that you're working on, at the previous one. And so in a way, that's a voting system. Where Satoshi's paper, he called it one CPU, one vote. CPUs are no longer relevant. So we can just think of as one hash computation nowadays is one vote. Every blockchain system has some way of voting. Ethereum is moving to something called proof of stake, and we'll skip talking about that now because we don't really need to spend time on that. So the way miners vote for a solution is a valid block comes in, they check that it's valid, the fields match the number of zeros are satisfactory. So just move on to working on the next one and put a pointer to the one they have accepted. You as an individual can say, I don't accept it. I'm going to work on my own. But if a majority of the miners agrees, that chain grows longer. It gets more computational proof and hence heavier. By heavy, we mean the computational weight of blocks. How many zeros are enough? That's tied to a parameter called difficulty or bits. We saw that on the Explorer. There's this number which is a float here, and it's related to an integer called bits, which we use in the hash computation. That determines how easy or hard it is to find a block. This number is readjusted every 2,000 blocks. So it's based on a moving average. And the idea is to make the difficulty larger or smaller so as to keep the average block time to about 10 minutes. Of course, some block just by chance will be mined in 2 seconds, and some will take a half hour, but the average is about 10 minutes. Money creation, this is the part that I think most of you know, is whenever a miner creates a new block, they earn 6.25 BTCs currently. It used to be 50. It halves every 210,000 blocks, about 4 years. Currently, it's 6.25. And of course, they collect fees from all the transactions. So in the block we saw in the Explorer, the block had 2,834 transactions for a total fee reward of 5. Let's convert this to dollars. Oh, the wrong slide. Anyway, so the rewards are 6.25 BTC plus a variable component for the transaction fees. By convention, the miners create a special transaction called a coin-based transaction, and that creates a new coin which has these rewards in it. And you can see that in our block. That's a block. These are the transactions. That's the coin-based transaction. Let's look at its hash. It has no inputs because it's a special transaction. It has all these opcodes. There's no inputs needed. And it has these outputs. Oh, while we are here, I can show you a little bit. So this miner in the output has included some op returns. Just like if you write a C program that ends in return 0, nothing else, well, that program is not going to do anything. So that's what these Bitcoin script op return means. It's not really processed, but it allows people to put arbitrary data in the blockchain, just like you saw the message from Satoshi in the Genesis block. So let's look at one message here from transaction number 3 in position 0. And I'm highlighting this because it's related to the folks I work for. We had so we had a hex converter somewhere. Well, I hope it doesn't show up any funny sites. That's the data from that Coinbase transaction, and you see it translates as RSK block and then some binary data. So this is us, the RSK blockchain, piggybacking on the security of Bitcoin by imprinting tags of our blocks in not every Bitcoin block, but some of them. Because Bitcoin is very hard to attack, so we tie our security in a process called merge mining, which you will probably learn about later in the course. Time check, 5:55. So quick stop on money supply. If you do the calculations on how many Bitcoins there are in the new transaction, 6.25, and that's going to be the same for the next 4 years, and then it's going to get half again. You use the geometric series formula and come up with a theoretical maximum of 21 million Bitcoin as the total supply possible. And I forget when we will reach that, but it's in several decades from now. Maybe as an economist, I should remind you, this has nothing to do with inflation economics. In blockchain, people use inflation just for the supply of the cryptocurrency, how much Ether or Bitcoin there are. It's got nothing to do with inflation in economics, which is about the price level of goods and services. Let's skip a few slides because I think the main I think this is something that's mentioned before, but it's worth repeating. Even if a majority of miners become dishonest and attack the chain with 51% majority attacks, all they can do is spend some of their own past coins. They cannot steal other people's coins, and you should know why. Anyone venture a guess why the miners, with no matter what the computation power is, cannot steal other people's coins? Any guesses? We can stop for maybe 5 seconds.
I believe you need the private key to access your coins, right?
You need the keys so you can sign. For spending requires signatures, absolutely correct. Even if you have all the computation power for hashes, you don't have access to other people's keys, so you can't sign their UTXOs. Thank you very much. So we've been at this, it's 5:57. Let's go on to this important bit, and then maybe we can decide if we want to keep going to other stuff. So the issue at hand is verifying how a transaction was included in a block. You send a transaction using an app on your smartphone. That smartphone obviously does not have all of the Bitcoin network's data or processing power. How would you figure out that the app says money was actually sent? So once we send a transaction using an app, the app will give us a transaction hash, which is a hash of some data of some fields within transactions. We will not get into details of how transaction hashes are created. But what we need to know is a transaction hash that we want to verify and the block number in which it was included. Okay. And the idea in Satoshi's paper is called SPV, Simple Payment Verification, is based on 2 concepts. One, the app that you're using only needs to store block headers, not entire blocks. The entire blocks can be pretty big. I mean, this one here, for example, the block size is 1.4 megabytes. Okay. So the block is 1.4 megabytes, and if that was block number 650, 750, so you can't store a million of those on your phone. What you can store on your phone are just the headers, because those are just 80 to 100 bytes each. So the first idea is use block headers only for these simplified payment verification proofs, and the second part is something called a Merkle proof. Merkle trees, very quickly, are binary trees. You are computer science students. You guys know what binary trees are. These are binary hash trees. So all the values in every node in a tree is just a SHA-256. Being Bitcoin, these are double SHA-256. Starting at the very bottom of the tree, the leaf nodes are hashes of all the transactions in a block. The parent, so one level up in the tree, is just the hash of its 2 children. We can call them the left and the right. If there are an odd number of leaves, then we repeat them. And then we repeat the process until we get to the root of the binary tree. the root is included in the block header, and it's called a Merkle root. Example, let's say we only have 2 transactions from users, and the miner includes a Coinbase transaction for themselves. So this block only has 3 transactions. Each one gives us a hash, so we have 3 hashes. We want to have an even number of hashes at the end, so we'll repeat the H2. And the way we form the tree is these are the 4 hashes. The first 2 will give us 1 parent hash. These 2 will give us another parent hash. Then we hash those 2 parents to get a root, because that's just how deep this tree is. And that's a Merkle tree. And as you have seen from hashing, you cannot change anything about a transaction without affecting the hash. So changing a single transaction, if a transaction was not included, the hashes will not match. So that's a simple idea. It gets a little simpler, and we'll steal an image from some place here. This one is from Investopedia. If you search for Merkle trees, depending on the source, you'll find different images. This one has very simple notations, TA, TB. More CS-friendly ones will have a T0 for the Coinbase instead of TA. The idea is simple. Start with the Coinbase, write out the hashes of all the transactions. And in this example, the red one here is the transaction you are interested in, TD. To confirm that this one was added in the block, you do not need to know the transactions of all the hashes of all other transactions. All we need to do is reconstruct the path from your transaction to the root. So for that, we need to know the hash of the adjacent, the sibling. From that, we can compute the parent. We need to know the transaction for that second layer. Again, we can compute the parent. And then we need the hash of this side of the tree. So with just the hash for your transaction and 3 other hashes, we can verify that a transaction was included in a block. And that's called a Merkle proof. And this is how most smartphone-based apps, simple wallets work without access to full blockchain data. The general advice is to also wait a certain number of blocks. So typically people say 6 blocks. I personally, if I'm just spending a small amount, then a block or 2 confirmations are fine. If you're spending a large amount, then you want to wait more blocks. It's really the receiver's choice. You as the sender have nothing to do. Once you send the Bitcoins, they're gone. It's up to the sender to decide how many confirmations they want to wait before they think of your payment as verified and practically irreversible. So it's the receiver's choice, not the sender's choice. A couple of trick questions. What if a block has no transactions? Then your Merkle tree only has 1 node. The Coinbase transaction is always there. And so in that case, the hash of the Coinbase transaction will match. We can verify that quickly for the Genesis block. So there, and see the Merkle root is that hash for a 5E, and that's the same as the Coinbase transactions hash. So that was kind of cheating a bit. This happens, for example, not so much in Bitcoin, but it happens in networks like RSK, which are just starting out, not a whole lot of transactions. Miners still have to mine, so they just mine a block with no transactions. That's perfectly legitimate. Merkle trees also show up in other applications. Those of you who are fans of BitTorrent may have seen the updates made to libtorrent recently. So when you're storing a file on distributed file storage systems, your file is broken up into chunks, and those chunks are hashed and put in a tree, and that's how you can verify that your data was stored. You can only recover the parts you need and reconstruct the files. Lots of exciting stuff happening on Swarm and the interplanetary file system, which we won't get into, but I'm sure you'll see them in your course later. 604. I think this is a good time for me to shut up and just see where we should go from here. We have already talked about tie breaking. If 2 blocks arrive at the same time, then whichever one has more computation wins.
I personally think this is excellent. Let's continue. And I mean, if you're available, let's even finish the slides. I think these are really valuable for everyone. And for those of you who need to have other commitment at this point, please, you may drop off, and I'll post the slides and the recording on the website. So I mean, the slides are already there, and I will put the recording too. So, but yeah, if possible, I think it'd be great to finish it because I think it's very nice.
Okay, so just wait 5 seconds for folks to kind of get to other things they have to, and we will continue. I don't think I have a whole lot and deleted a bunch of stuff because I wasn't sure how much time it'll take. So just stop here for a second, let that float in space. This is kind of related to the double shot question, but it's not a complete answer. But here's an approximation of what the probability is of a hash satisfying any given target. It's 1 over 2 to the 32. The 32 is coming from bytes. And D is called difficulty. When Bitcoin started, the difficulty was 1. And now the difficulty is 1. Wait, oh, that's block 0. Block 0, difficulty of 1. And now the difficulty is, so that's not a billion. That's like, we have a trillion, 19 trillion. So this gives us an idea how difficult it is to hit a target. It's readjusted every 2 weeks. And the idea is to keep the blocks coming at an average rate of about 10. Payoffs from mining. If you're very lucky and you have access to mining equipment, like an Antminer or something, ASIC, I'm not sure if you can put one in your dorm room, someone will find out. But let's say you have a mining, some kind of apparatus that can produce hashes at the rate h. These are double shot hashes of blocks per second. And you mine for a time t with difficulty d, then given that probability on the previous slide, this is the approximate number of blocks we will find. So the probability times the hash rate times the time for which we are mining gets a number of blocks. Multiply this with the reward, which is 6.25, and we get an idea of how profitable mining is. Oh, I think I had the figure somewhere. I don't have it anymore. But here are some numbers. Using that formula, if you have equipment that can do 1 gigahash, which is really nothing these days, professional mining equipment can do, let's see if I have a link to, I had a link to ASIC unit here. This is an advanced mining, I mean, it's not a computer, you attach it to your computer. All this does is it's hardware specifically designed to compute double shot hashes of Bitcoin headers. It costs $2,400, and if you put this in your dorm room, someone is going to notice because one, it consumes about 3 kilowatts, so it's like running three space heaters in your room, and it also weighs about 30 pounds. But the generating capacity is 110 terahash per second. That's compared to, say, what can I do on my laptop? My laptop is 1.5 gigahertz, so maybe I can do 600,000, maybe a million hashes in a second. This thing can do 110,000 terahashes. These are numbers that I often lose context for how big they are. But to remind you, the Bitcoin network was doing those 75 billion things that we talked about earlier. And so even if you were to get your hands on an Antminer S19, you would still only be 1 of a millionth of the computation power of the whole network. So even with this machine, you're not very likely to make a very steady income. So what people do is they become part of mining pools. And because solar mining just has too much variance in how frequently you find Bitcoins, you join a pool. We already talked about the shares used for accounting and mining systems. And shares are hashes that have fewer zeros needed out in front. So the manager just counts how many valid shares you have produced, and the more. Okay, so I guess that wasn't a question. And depending on the number of valid shares, pool members get distributed the earnings. So I estimate the electricity cost of running that one SA19 miner in Seattle. Electricity prices is about $10 a day. So that's something else that if you put this in a dorm room, someone will notice is your utility bills are going to be really high, in addition to the 3 kilowatt of heat that's going to be generated. We talked about this is what the network is doing. And so that gives us an idea of how much money is being spent in just electricity overall. So about $10 million a day. Most of it is, depending on the source, it's hydro in China and hydro in Bitcoin miners in Washington and Oregon. And those in West Texas are mostly using wind. But it's just natural for miners to float into spaces where energy is cheap and not rely on gas power or coal power.
How much of the volume of the payment actually gets transferred per day? $10 million to mine? Do you know any cash flow?
I would imagine more. I expect the 10 million to be just energy costs.
Yes.
They're also spending on thousands of these miners, and they put them in cages inside data centers, the cooling equipment, and so people costs. I saw an estimate somewhere that those overheads are about the same as the energy costs. So pro rata, if this is 10 million a day, then maybe 20 million overall.
And you know how much cash flow, how much transaction, how much money gets transferred per day?
No, I don't know that.
I was just wondering.
No, but I think one way to check the numbers, I don't know about the distribution, but one way to check the numbers is to just, we know how much Bitcoin is being generated every day, 6.25 every 10 minutes. And so we multiply the number of blocks and rewards. Miners have a lock time. So when someone mines a block, they cannot immediately access those Coinbase funds. So people, I think they can use the time and follow the money and then get an estimate of how frequently the distributions are shared. But I don't have any numbers.
I see. So you said
Does that make sense?
No, it makes sense. It's about 900 Bitcoins generated a day. They are what, 10,000 each right now?
Yeah.
Okay. So multiply by 10,000.
So that's about 9 million then.
Yeah, that's about.
Well, if that's 9 million, then my numbers are off by a factor of 2. It can't be spending 10 million on energy if the total value of Bitcoins is 9 million. So I think my numbers are off by at least a factor of 2. Maybe it's 5 million a day and not 10 million a day.
Yeah, but did you know how much the volume of the actual transaction people do? So is it like, so $10 million, let's say, is being generated, $10 million worth of Bitcoin being generated, and how much monies get actually pushed around different accounts to kind of get a transaction, overall transaction cost as a percentage of the flow?
That will be hard to get because for one, for example, in this block, we see the total amount of Bitcoins moved. That's close to 6,000 Bitcoin, and the Coinbase that the miners are playing with is only around 7 or 8 Bitcoin. So a lot of transactions, unless we go and look into how much of this is about just miners, I don't know.
I see.
But the size of the overall market is way bigger than the number of Bitcoins being created.
I see.
Right, just this one block in 10 minutes has 6,000 Bitcoin. So that's 100 times, that's 1,000 times bigger than the miners. But there is a separate market for what are called pristine Bitcoins. There are some banks in Europe and in Hong Kong that they buy Bitcoins from miners. They pay a premium for Bitcoins that have never been used before. And they sell for about 15% premium over the market rate. It helps them avoid some money laundering laws because they can prove that their Bitcoins did not come from any dirty money laundering operations. So that's called a pristine Bitcoin project. And 616, I think this is a good place for us to stop.
Sure. So also my calculation was slightly off. So I think it would be 15 million Bitcoin generated per day.
15?
15 at $10,000 price. I don't know what the price is. I just put 10,000.
So if it's 15 million, then I would still think the energy costs, the electricity costs are about a half. And the margins are still kind of small for miners. They just make it mostly on volume.
I see.
And so, yes, I think we should wrap this up now.
Sure.
There's more. We have covered the main ideas really were about proof of work, how the hashes are computed. That gets us a way to add to the chain. And it's also a voting system. And then proving that the transaction was included using Merkle proofs. I think if folks can just focus on those three takeaways, the rest of the details can really be dropped and they'll come back. But the main three ideas are Merkle trees, the proof of work computation, and the voting, the majority. So if there are no further questions, I think we can wrap it up.
Yeah, so I think it was wonderful. Thank you so much. It was excellent. So let me just, I guess we have see the final round of questions. Any other thing that you wish to ask? I think we're all very appreciative. I think it was just a wonderful lecture, very informative, and I think we touched them upon many interesting topics. So I think
it's a rabbit hole. I mean, I start my actual job, and the last 4 days I've been reading about Bitcoin, preparing to talk to you guys. It's been great. I enjoyed it very much too. Thanks for having me.
Thank you so much. Oh, thank you for delivering this wonderful lecture.
All right, I'm gonna pop into some of your other. You meet every Thursday around the same time.
Yes, and Tuesdays.
And Tuesdays, so.
Yeah, so the schedule is on the website. So yeah, you have the link, and
yes, please.
Sometimes I think there's 2 sessions that we have it on Fridays as well. So yes, absolutely, anytime. Please join us, and we would be happy to have you.
Awesome. Thank you so much. Thank you, everyone.
Thank you.
Goodbye.
Thank you so much.
Thank you.
Thank you. Bye.
Bye. Bye.